In today's story, we're going to look at interdependence. The first aim is explain what food chains show us, then explain the purpose of a pyramid of biomass, and then finally explain examples of mutualism and parasitism. Now, as an aspiring young teenager, I'm sure one of your chief goals is to gain independence from your parents. However, don't trick yourself into thinking that you ever will become truly independent. Take, for example, the polar bear. The polar bear leads one of the most solitary lives in the animal kingdom. It can quite happily exist without any company for long durations of time. However, even the polar bear is dependent on other organisms for survival, for example, for food. Humans, however, in general are specialists. We specialize in certain fields. For example, I specialize in the field of teaching. But if I had a problem with electrics or with plumbing, I'd need to call a specialist in to help. In fact, even the food we eat, we rely on other people to catch, kill, and transport that food to stores so we can go and purchase it. In other words, yes, we're very far from being independent. And that's okay, because that's the point of this lesson. No organism is truly independent. We depend on other organisms for our survival, and that is what is meant by interdependence. Take this picture here of a crocodile and the plover bird. It may immediately look like the crocodile's about to have a nice meal. However, this bird is actually doing this crocodile a service. The crocodile willingly opens its mouth, and then the plover bird climbs inside and starts picking away at parasites and bits of food debris that have lodged in between the teeth of the crocodile. The plover bird gets food and nutrition, and the crocodile gets a healthy set of teeth. This is an example of mutualism, and it's just one form of interdependence. But the most common form is certainly the food chain. Now, I'm sure you're no stranger to food chains. You learn about food chains in primary school. But what do they actually show us? Food chains don't show us what eats what. Instead, they show us the direction of energy flow within a specific habitat. And therefore, the direction of the arrows definitely matters, because energy flow can only happen in one direction. So let's look at an example. Here I've got a very simple food chain with grass being fed upon by rabbits, which are fed upon by foxes. The first hurdle is to basically develop the correct terminology. Every feeding level of the food chain is referred to as a trophic level. So this is one trophic level, second trophic level, third trophic level. In almost all examples, plants will start off a food chain. You may remember the tutorial on hydrothermal vents where that isn't the case, but generally most organisms rely on the sun as their source of energy. So plants take the solar energy and convert it into sugars. This supplies them with energy for growth and so on. Their ability to make their own food gives them the term autotroph, self-feeder. We can also call plants producers, because they produce food for the rest of the food chain. Then the energy gets transferred to the next trophic level, in this case the rabbit. Now I've given the rabbit the term heterotroph. That's the opposite to autotroph, because their survival depends on feeding on other organisms. So every other organism apart from the producer is a heterotroph in a food chain. So the next trophic level up from producers will be the primary consumers, then the secondary consumers, in this case the fox, and it could go on to tertiary consumer, or sometimes we call them the top carnivore. So just to recap, plants receive energy in the form of sunlight. That energy gets passed on to the next trophic level, the primary consumers. Then that energy gets passed on to the next trophic level, the secondary consumers. But this process is far from efficient. We can see the 100 joules, for example, stored in the plant. Only 40 joules of that gets transferred to the rabbit, of which only 4 joules gets transferred to the fox. This is why food chains can't go on forever. There just won't be enough energy to go around or to support a greater number of organisms. Now, if you're good at physics, you'll know that energy is never lost or destroyed. It must be transferred. So how is it being transferred out of this system? So energy is stored as physical matter that makes up the organism, but not necessarily all of that organism gets eaten. For example, the roots underneath the soil are unlikely to be eaten. So because not all of the organism is actually eaten or digested, for example, grass is mainly cellulose. Cellulose is very tough to digest. In fact, a rabbit has to eat this grass, then it has to allow the grass out the other end, and then it eats its own droppings to basically try and extract that nutrition. So some energy is lost from the system purely because it isn't eaten or digested. For example, we can't digest fiber. Also, of course, the organism needs to use some of that energy for growth and so on, to carry out metabolic processes such as respiration. So you can see why now only a portion of that energy gets transferred to the rabbit. And then the cycle repeats itself, so again, energy is lost through respiration and also through waste, through animal waste. And also remember, the fox may not necessarily eat all the bones of the rabbit. So there'll be less energy going forward onto the fox. And again, some will be lost as respiration and waste, and some may not be eaten or digested by the next trophic level. So it's a pretty standard exam question to ask you why is not all the energy transferred from one trophic level to the next. And just remember some of these staple answers. Not all of it's digested. Some is lost as waste. Some is lost through respiration. It's also important to know that these molecules of food that pass through the food chain must get recycled as well, so that the whole process can start again. So for example, plants will take in elements such as carbon and oxygen, hydrogen and nitrogen from the air and from the soil. They will then form more complex molecules from these base elements. As other organisms can't really do this, they rely on plants to manufacture these complex molecules, and then these molecules get passed along the food chain. But how do they get recycled? Well, when an organism produces waste or dies, even plants die, those nutrients or those molecules get returned to the soil. This allows certain organisms called decomposers or detritivores to break down these molecules back into their constituent parts. This process is called decay. Common examples of decomposers include fungi and bacteria, which are already in the soil. So plants acquire the elements they need from the air and the soil. They then manufacture complex molecules which get passed along the food chain, and then when organisms die or produce waste, decomposers act on those molecules to bring about decay of those molecules to bring them back to their constituent parts so the whole cycle can start again. In a stable community, the materials taken out of the soil are used and balanced by those that are put back in. It's quite common now for people to make their own compost using compost bins. Normally these involve a mesh which allow lots of oxygen in, which helps the decomposers decay at a faster rate, and also the warmth produced by this reaction, this decomposition reaction, also accelerates the process. If you want to make really good compost, it's a good idea to shred up the material first to increase the surface area, so again decay happens at a faster rate. The compost can then be used to grow new plants. So that is what a food chain shows us. Now, if you remember that food chains show us the direction of energy flow through a habitat, but just looking at a food chain doesn't give you much of an idea of how much energy is being passed on from one trophic level to the next. For that, we need something called a pyramid of biomass. There are a number of pyramids on offer. You can have a pyramid of energy, a pyramid of biomass, and a pyramid of numbers. I'm going to start off just by showing you pyramid of numbers and its limitations. To make this pyramid, it's simple. You just count the number of organisms at each trophic level and then just produce a bar which represents that number. Now in this food chain, this all makes sense. You'd expect this to be the largest trophic level and therefore containing the most energy, and then it supports fewer in number, and that level supports fewer in number still. So if you remember the energy going down from 100 joules to 40 joules to 4 joules, this pyramid sort of directly relates to that. But sometimes pyramid of numbers can be misleading. Take for example this food chain where you have an oak tree supporting caterpillars which support thrush. Now an oak tree obviously contains a lot of energy, but if you were to use a pyramid of numbers it would look a bit odd because there's only one oak tree. So it looks like very little energy supporting a trophic level which requires a lot more energy. This is exactly why we use pyramids of biomass. With pyramids of biomass, we take the combined mass of every organism at each trophic level. So this is the mass of the oak tree, this is the combined mass of the caterpillars, and this is the combined mass of the thrushes. That's because physical matter mass is a good indicator of energy store. So you can see that the pyramid of biomass sorts out the error that the pyramid of numbers presents. In an exam, you will need to know how to construct pyramids of biomass from data. So here's a data table, and we see the trophic level on the left with producers here, primary consumers here, and secondary consumers here, and then combined mass of the organisms within that trophic level. So 1,000 kilograms for the producers, 500 kilograms for the primary consumers, and 100 kilograms for the secondary consumers. You'll also most likely be given a bit of graph paper to do this on, so you have to devise your own scale. Here I've decided that each small square here is equivalent to 100 kilograms of biomass. It also helps if you mark a central line, because remember you have to count numbers or values away from the central point. This is what makes this a little bit trickier than a bar chart. So let's start off with the producers, which have a combined mass of 1,000 kilograms. Here I'm going to take this bar and I'm going to put it here. You can see because every small square here is 100 kilograms, we have 100, 200, 300, 400 and 500, and obviously 500 the other direction, which gives us 1,000. Now the next trophic level is 500 kilograms, so let's do that one. So in this case, we need 250 on each side, so when you add them together, it makes 500. So you have 100, 250, halfway between the 100 square, and then 100, another 100, another 50. So 250 plus 250 is 500. Now it always gets a bit more fiddly the smaller the number is. So next number is 100, we just need a 50 on either side. That's halfway between the 100 square. So let's just take our final trophic level and put it there. And there we have our completed pyramid of biomass. So if you understand how a pyramid of biomass shows energy flow through a habitat, then you understand the purpose of a pyramid of biomass. Now let's look at two other forms of interdependence. The first is a mutualistic relationship, and then secondly, parasitic relationships, so mutualism and parasitism. Mutualistic relationships can be summed up with this little icon here, 2 pluses, because both organisms benefit, and parasitic relationships can be summarized as a plus minus because one organism benefits in the relationship and the other one certainly doesn't. In fact, its fitness is reduced as a result of the relationship. So mutualism or symbiosis involves one organism giving something to the other organism that it needs and vice versa. Whereas a parasite is an organism that lives on another host. The parasite will benefit from this relationship, but at the cost or the expense of the host's health or fitness. So if you ever have to explain what a parasite is, you must talk about it living off another host and the host's fitness being reduced or its health being reduced. Just remember plus plus and plus minus. Here are some examples you need to know about mutualism. The oxpecker, for example, and the buffalo. The oxpecker is a small bird that sits on the buffalo's back and feeds off the parasites. Therefore, the buffalo's health is improved and the oxpecker gets some food. In a very similar kind of relationship, we have the cleaner fish, which acts upon larger fish doing exactly the same thing, feeding on the parasites and improving the health and fitness of the larger fish. Two higher level examples you need to know is that of nitrogen fixing bacteria, which you'll also learn about in the nitrogen cycle. These are tiny bacteria that live in the swollen root nodules of certain plants called legumes. What they can do is take atmospheric nitrogen and fix it into compounds called nitrates. That's when you react the nitrogen and the oxygen to make a mineral salt which the plant needs for growth. In return, the legume photosynthesizes and produces sugars to feed the bacteria, as well as providing a home for them to live. And you may have seen this one before, but we have chemosynthetic bacteria that live inside tube worms, giant tube worms near hydrothermal vents. The tube worms provide a shelter and a source of chemicals which the bacteria then turn into organic molecules which feed the tube worms and themselves. If you want to understand that relationship in more detail, please watch the tutorial on adaptations to extreme environments. Now here are some examples of parasitic relationships. So obvious ones are, for example, fleas, which live on dogs and suck their blood, reducing their fitness. So the flea benefits and the dog does not. In fact, it's harmed in the process. Exactly the same for the next relationship. We have head lice that live on basically the scalps of humans, sucking their blood, so our health and fitness is lowered, whereas the head lice benefit. Tapeworms are basically long, large, flat worms that live in our gut and they feed off our food. That means we do not get all the nutrition from our food and our fitness is lowered. In fact, it can often be a cause of quite dramatic weight loss. In fact, it has been reported that some supermodels or people who are interested in weight loss have actually swallowed tapeworm eggs to develop tapeworms in their gut to actually help them lose weight quickly. I need to stress this is a terrible idea. For one, we're talking about a huge worm, a worm which can grow to exceptional lengths with hooks to attach itself and suckers to attach itself to your gut, feeding off your food supply. And if that doesn't gross you out enough, the eggs can also get into places where they're not supposed to go and the worms can start developing in areas they shouldn't. This can actually lead to death. So please, please, please stay away from the tapeworm diet. Exercising is a lot more fun anyway. And finally, the romantic plant, the mistletoe, which is always made famous around Christmas time. Mistletoe is actually a parasitic plant. It latches onto trees and buries its roots into the vascular system of the plant and starts tapping away at their nutrients. As a result, the tree's growth is slowed and its health is generally reduced. So once again, the mistletoe benefits, the parasite benefits at the cost of the host's health. Parasites are quite honestly amazing things. They're disgusting and amazing. And if you just did a search on YouTube or Google, I'm sure you'd find some incredible examples of parasitic relationships. I'll just leave you with one. There's a parasite whose main host is a cat, but the parasite finds it quite difficult to get directly inside a cat, so what it does instead is it infects mice. And through infecting them, it actually changes the behavior of the mice. As a result, the mice now feel inexplicably attracted to cat urine, so they'll go and seek out cat urine and start hanging out in cat urine. Now, no surprise, cats also like the smell of their own urine. They use it for scent marking and so on. So it won't be long before a cat comes and gobbles up the mice, and thereby gobbling up the parasite. Genius. Also quite disturbing. And those are a few examples of mutualistic and parasitic relationships.